DDR1. DDR1 was the first generation of double data rate memory to become widely used in personal computers. It became popular in the early 2000s and replaced older SDR RAM technology with a more efficient way of transferring data. The main improvement was the ability to transfer data twice during each clock cycle, once on the rising edge and once on the falling edge of the clock signal. This allowed DDR1 to provide more memory bandwidth without requiring the memory clock itself to run twice as fast. DDR1 was available in different speeds and capacities for its time, with common modules ranging from a few hundred megabytes to around 1 gigabyte. These capacities may seem very small today, but they were suitable for the operating systems, applications, and games of the early 2000s. DDR1 was commonly used in desktop computers, laptops, and early gaming systems. It provided a significant improvement over traditional SDR RAM, but its bandwidth and capacity were eventually no longer enough for faster processors and increasingly demanding software. DDR1 also used more power than the generations that followed. As computers continued to become faster and more complex, the industry needed memory that could deliver higher speeds while using less power. That led to DDR2. DDR2 was introduced as the successor to DDR1 in the mid-2000s. It kept the basic double data rate principle of transferring data twice per clock cycle, but introduced improvements to the internal memory architecture that allowed it to achieve higher effective data rates. Compared with DDR1, DDR2 could operate at significantly higher speeds while also reducing its typical operating voltage. DDR1 generally operated at around 2.5 volts, while DDR2 typically used around 1.8 volts. This reduction helped lower power consumption and heat generation. DDR2 also increased the internal prefetch size from 2 bits in DDR1 to 4 bits. In simple terms, this allowed the memory to prepare more data internally for each memory operation, helping it achieve higher effective transfer rates without requiring the external clock to increase by the same amount. DDR2 commonly reached effective data rates from around 400 to 800 megatransfers per second, giving computers considerably more bandwidth than DDR1. It also supported larger memory capacities, which became increasingly important as operating systems, applications, and games became more demanding. DDR2 became common in desktop computers, laptops, and gaming PCs throughout the mid and late 2000s. It offered a clear improvement over DDR1 in speed, efficiency, and capacity. However, as processors became faster, even DDR2 eventually struggled to provide enough bandwidth. This created the need for another generation that could deliver higher performance while continuing to improve power efficiency. That generation was DDR3. DDR3 became widely used around the late 2000s and remained popular for many years. It continued the improvements introduced by DDR2, providing higher speeds, lower power consumption, and support for larger memory capacities. Compared with DDR2, DDR3 generally operated at a lower voltage. Standard DDR3 typically used around 1.5 volts, compared with around 1.8 volts for DDR2. This made DDR3 more energy efficient and helped reduce heat, which was especially useful in laptops and other portable devices. DDR3 also increased the internal prefetch size from 4 bits in DDR2 to 8 bits. This allowed the memory chips to move more data internally for each external memory clock cycle, helping DDR3 achieve higher effective data rates. Common DDR3 memory was available at effective speeds ranging from around 800 to 2,133 megatransfers per second, depending on the specific module and platform. The increase in speed and capacity made DDR3 much better suited to newer processors and more demanding software. Computers could handle larger applications, more intensive multitasking, and modern games more comfortably. DDR3 was found in almost every type of mainstream computer during its era, from everyday office PCs and laptops to gaming computers and servers. DDR3 also became available in lower voltage versions, such as DDR3L, which typically operated at around 1.35 volts. These versions were designed to improve energy efficiency and were especially useful in laptops where lower power consumption could help extend battery life. Compared with DDR2, DDR3 offered higher bandwidth, lower voltage, improved efficiency, and larger practical memory configurations. But as CPUs continued to become faster and software demanded even more memory bandwidth, DDR3 eventually reached its limits. The next major step was DDR4. DDR4 became mainstream in the mid-2010 and brought another major increase in memory speed, capacity, and efficiency. Compared with DDR3, DDR4 supported much higher effective data rates. Early standard DDR4 memory started around 2,133 megatransfers per second, while later modules became available at 2,400, 2,666, 3,200, and much higher speeds. This increase in bandwidth made DDR4 a better match for newer and faster processors, especially in systems designed for gaming, content creation, and other demanding workloads. Standard DDR4 generally operates at around 1.2 volts, compared with around 1.5 volts for standard DDR3. The lower voltage helped reduce power consumption and heat while maintaining higher performance. Another major improvement was memory capacity. DDR4 made larger amounts of RAM much more practical, with configurations such as 16, 32, and 64 gigabytes becoming common in desktop PCs and workstations. This was useful for modern games, video editing, 3D applications, professional software, and heavy multitasking. More memory allowed computers to keep more data available without relying as heavily on slower storage. DDR4 became the standard choice for many desktop computers, laptops, workstations, and servers throughout the late 2000s and into the early 2020s. It was also extremely popular in gaming PCs because modern games and applications could benefit from its higher bandwidth and larger available capacities. However, as processors continued to improve, the demand for memory bandwidth and capacity increased again. DDR4 eventually needed a successor that could push these improvements even further. That successor was DDR5. DDR5 is the newer mainstream generation of double data rate memory and began appearing in consumer computers in the early 2020s. It was designed to provide significantly higher data rates, greater memory capacity, and improved efficiency compared with DDR4. One of the biggest improvements is speed. DDR4 commonly started around 2,133 megatransfers per second, while DDR5 starts at around 4,800 megatransfers per second. Modern DDR5 modules can reach considerably higher speeds, providing much more potential memory bandwidth. This extra bandwidth is useful for modern processors and demanding workloads such as gaming, content creation, professional applications, and other tasks that need to move large amounts of data quickly. DDR5 also continues the trend of reducing operating voltage. Standard DDR5 generally operates at around 1.1 volts, compared with around 1.2 volts for DDR4. While the difference may seem small, lower voltage can help improve efficiency, especially in systems with large amounts of memory. Another important improvement is the internal organization of the memory module. A typical DDR4 module provides one 64-bit memory channel, while DDR5 divides this into two independent 32-bit channels within the same module. Together, they still provide the equivalent 64-bit data width, but the smaller channels can handle memory operations more independently. This change can improve memory access efficiency and help the memory controller handle multiple requests more effectively. DDR5 also supports much greater memory densities than DDR4. This allows modern systems to use significantly larger amounts of RAM, which can be particularly useful in high-performance desktops, workstations, servers, and other systems that require large amounts of memory. However, DDR5 is not backward compatible with DDR4. A DDR4 motherboard cannot simply use DDR5 memory, and a DDR5 motherboard cannot use DDR4 modules. The physical design, electrical requirements, and memory architecture are different. This means that upgrading from DDR4 to DDR5 usually requires a compatible motherboard and processor platform, rather than simply replacing the RAM sticks.